Tonight, we begin a journey, a quiet, contemplative drift through the cosmos to uncover a truth so profound it reshapes our understanding of home itself. For nearly 70 years, a fundamental constant in our cosmic address, the very size of our galaxy, the Milky Way, has been profoundly, almost unbelievably, miscalculated. We have, for generations, been teaching, charting, and even dreaming about a galaxy that was, in reality, only half the true scale of the majestic spiral we inhabit. Imagine, if you will, the quiet hum of a distant star, its light slowly, patiently, making its way across the vast interstellar void, only to reveal that the map we've been using, the grand blueprint of our celestial neighborhood, was drastically incomplete. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. The consensus, for so long, held that our home galaxy stretched approximately 100,000 light-years from one elegant spiral arm tip to the other. This measurement, once considered a cornerstone of modern astronomy, was a figure etched into the pages of countless textbooks, depicted in every classroom diagram, and calculated in untold scientific papers. It was the accepted reality, a foundational piece of our understanding of the universe. Yet, with the advent of revolutionary new technologies and a deeper, more nuanced approach to cosmic observation, we are now faced with a staggering revelation. The Milky Way is not 100,000 light-years wide. It is unequivocally twice that size, perhaps even more expansive than our current estimations can fully grasp. This isn't merely a minor adjustment, a slight tweak of a few percentage points on a cosmic ruler. This is a complete categorical re-evaluation, a fundamental shift in perspective that demands we reconsider everything we thought we knew about our galactic home. We have been living, quite literally, within a structure that is double the scale we previously conceived, an immense, intricate system of stars, gas, dust, and, most importantly, invisible dark matter that dwarfs our prior mental models. Think of it as discovering that the quaint, familiar town you grew up in, a place you thought you knew intimately, actually extends far beyond its perceived borders, sprawling into vast, previously uncharted territories, rich with hidden landscapes and unseen neighborhoods. The implications of this colossal correction ripple outward, touching upon almost every facet of modern astronomy. It compels us to re-examine how we measure the universe at large, recalibrating the very tools and methodologies we employ to chart the distant cosmos. It fundamentally alters our timeline for future cosmic events, notably the much-anticipated gravitational embrace with our neighboring giant, the Andromeda Galaxy. And, perhaps most poignantly, it dramatically expands the sheer volume of space within our own galaxy that might potentially harbor life, profoundly shifting the probabilities in our ongoing, silent search for companionship among the stars. This is the story, a quiet, unfolding narrative of the biggest correction in modern astronomy, a tale of scientific humility and astounding discovery. So, let us prepare ourselves, allowing our minds to drift across these incredible distances as we begin to unravel the threads of this magnificent, newly revealed truth. If you were to open an astronomy textbook from just a few years ago, or perhaps even one still lingering on a dusty shelf in a school library, and turn to the section illustrating the Milky Way, you would invariably encounter that familiar, elegant spiral diagram. It would be adorned with neat, precise measurements confidently proclaiming a diameter of roughly 100,000 light-years. This image, deeply ingrained in the collective consciousness, was the bedrock of our galactic identity. However, with the quiet whisper of new data, we now understand that this diagram is not just a little bit off or slightly outdated, it is, in a profound and undeniable sense, completely wrong. The error isn't a subtle oversight, a minor rounding mistake in the grand calculations of the cosmos. No, It's a fundamental misrepresentation, a depiction of our galaxy at merely half its actual, breathtaking size. Every glossy poster gracing classroom walls, every meticulously crafted documentary animation portraying our galactic home, every Wikipedia diagram you might have trusted implicitly, all of them, without exception, presented a Milky Way that was, in reality, only half the magnificent entity we now know it to be. Imagine relying on a map of a vast, intricate forest, only to discover that the map stops abruptly at what you thought was the edge, while the forest itself continues to stretch for miles and miles beyond, teeming with unseen life and unexplored pathways. That, in essence, has been our predicament, our collective astronomical blind spot. For years, a subtle, persistent unease had settled among scientists, a quiet, almost imperceptible tremor in the bedrock of their understanding. They sensed, deep within the intricate web of collected data, that something wasn't quite right. The pieces of the cosmic puzzle, painstakingly gathered over decades, simply refused to fit together in a harmonious whole. These were not glaring inconsistencies, but rather fragments of information, faint whispers from the galactic fringes, anomalies that stubbornly defied the established models. Stars, for instance, at the very edges of what we considered the galactic boundary, were observed to be moving with an inexplicable velocity, far too swiftly for the gravitational pull of a 100 Zollard light-year galaxy. It was as if runners on an invisible track were maintaining Olympic speeds long after the track itself was supposed to have ended. Similarly, the delicate orbits of the Milky Way's satellite galaxies, those smaller, ethereal companions that gracefully circle our larger home, presented another perplexing riddle. They were observed to be orbiting at distances far beyond the gravitational reach predicted by the old, smaller galactic model. It was akin to witnessing distant moons orbiting a planet at distances that, according to our calculations, should cause them to simply drift away into the cold, empty expanse of space. And then there were the mass calculations, complex equations designed to weigh the entire galaxy based on the movements of its constituent parts. These calculations consistently failed to balance, leaving an unsettling deficit, a substantial amount of missing mass that defied explanation within the confines of the established 100 Zollard light-year paradigm. These were the subtle hints, the quiet warnings, that something grander, something more immense, lay just beyond the veil of our current perception. The scientific community, a vast collective of curious minds, continued its patient work, building ever more sophisticated instruments, pushing the boundaries of what could be observed and measured. And then, slowly at first, but with increasing momentum, the new measurements began to pour in, a deluge of fresh data that would irrevocably alter our understanding. The Gaia spacecraft, a sentinel in the blackness of space, meticulously tracked the precise movements and distances of over 1 billion stars within our galaxy, providing an unprecedented three-dimensional map of our celestial home. Its data began to whisper tales of a much larger, more dynamic system. Then came the James Webb Space Telescope, a revolutionary eye peering into the infrared spectrum, capable of seeing through the thick, obscuring dust clouds that had long hidden vast swaths of our galaxy from optical view. Webb's observations began to reveal entire populations of stars and complex structures in regions previously thought to be empty, pushing the perceived boundaries of the Milky Way further and further outward. Concurrently, an array of powerful radio telescopes, their colossal dishes silently sweeping the heavens, meticulously mapped the distribution of hydrogen clouds, those vast, diffuse nurseries of star formation, particularly at the extreme fringes of the galactic halo. Each new instrument, each fresh data set, consistently revealed the same shocking pattern, a consistent narrative that echoed across the different observational techniques. The Milky Way, our home galaxy, extends far, far beyond where we had so confidently drawn its supposed edges. The problem, it turns out, was not rooted in carelessness or a lack of intellectual rigor on the part of astronomers. Quite the contrary. The challenge, the profound hurdle that stymied generations of brilliant minds, lay in the inherent difficulty of attempting to measure a structure as vast and intricate as our galaxy while being inextricably situated inside it. Imagine, if you will, the sheer impossibility of standing amidst the towering skyscrapers, the bustling avenues, and the labyrinthine alleyways of a sprawling metropolis like New York City, and attempting to accurately draw its precise boundaries. From your vantage point within the city's heart, the edges are simply invisible. You cannot ascend to a vantage point high enough to gain a comprehensive, external perspective. You are utterly surrounded by the vibrant, overwhelming tapestry of buildings, the dazzling, omnipresent lights, and the ceaseless symphony of urban life. This analogy, while still falling short of the true cosmic scale, perfectly encapsulates the predicament faced by astronomers for decades. We, as observers, are not granted the luxury of stepping outside our galaxy to gaze upon its full, majestic form. Instead, we are forever floating within one of its outer spiral arms, approximately 26,000 light-years distant from its luminous, enigmatic center. From this internal vantage point, we are, in essence, drowning in a dense, brilliant ocean of stars and obscuring dust, a celestial fog that severely limits our line of sight and distorts our perception of true galactic scale. It's like trying to map an entire ecosystem from the perspective of a single ant within it, surrounded by towering blades of grass and microscopic debris that block any panoramic view. The sheer immensity and internal complexity of our position made accurate measurement an exercise in profound difficulty, a challenge that demanded not just ingenuity, but entirely new ways of seeing. For decades, the standard approach to delineating the Milky Way's edges was remarkably straightforward, almost disarmingly so, given the profound complexity of the subject. Astronomers, with the limited tools at their disposal, focused their observational efforts on tracking the brightest, most easily discernible stars they could detect in every conceivable direction across the celestial sphere. Their reasoning was simple. Where these luminous beacons of stellar activity began to noticeably thin out, where the brilliant tapestry of stars appeared to fray and dissipate into the encroaching darkness, that was where they drew an imaginary line. This line, a demarcation based on visible stellar density, became the accepted boundary, the perceived edge of our galaxy. And so, with a certain degree of confidence, the pronouncement was made 100,000 light-years across. Case closed. However, as is so often the case in the grand theater of scientific discovery, the universe rarely conforms to our neat, simplistic human constructs. The galaxy, it turns out, does not possess a sharp, well-defined edge, akin to the precise rim of a dinner plate or the crisp boundary of a national map. Instead, its luminous presence, its stellar population, fades with an almost imperceptible gradient, gradually dissolving into the profound emptiness of intergalactic space. Stars do not abruptly cease to exist at a specific demarcation point. Rather, they scatter outward in increasingly sparse, ethereal streams and diffuse, ghostly clouds, like embers drifting away from a dying fire. And herein lay the profound oversight of those earlier, seemingly logical measurements. They primarily tracked only the bright, the obvious, the easily visible components of the galaxy, the brilliant, densely packed spiral arms, the glowing, energetic core, the prominent star-forming regions. What they fundamentally missed, what remained stubbornly invisible to their instruments and methodologies, was the colossal, all-encompassing halo of dark matter that wraps around the entire visible structure of the galaxy like an immense, ethereal shroud. This invisible, yet gravitationally dominant, material extends far, far beyond the luminous disk, fundamentally altering the true scale and gravitational influence of the Milky Way. The old measurements, in their focus on the radiant, tangible elements, were akin to measuring the visible tip of an iceberg while completely ignoring the colossal, submerged mass that constitutes its true, overwhelming bulk. They captured only a fraction of the reality, leaving the vast, dark scaffolding of our galactic home utterly unquantified. Then, a pivotal shift occurred, a quiet revolution in observational astronomy that irrevocably changed our perception of the Milky Way. Scientists began to focus their attention on tracking stellar streams. These aren't merely random scatterings of stars. Rather, they are the cosmic equivalent of archaeological records, immense, elongated rivers of stars, each one a relic, a remnant of smaller, less fortunate galaxies that the Milky Way, in its inexorable gravitational hunger, devoured millions, even billions, of years ago. These stellar streams, like celestial fossil trails, continue to orbit majestically through the vast, silent reaches of space, their intricate paths meticulously tracing the true, undeniable gravitational pull of our colossal galaxy. When researchers painstakingly mapped these ghostly streams, a startling and undeniable truth emerged. They found these stellar rivers circling far, far beyond the previously accepted, supposed edge of the galaxy. Instead of dissipating at 100 Zalosan light years, these streams continued their ancient, silent journeys, their orbits extending to 200 Zalosan light years, and in some cases, even farther into the cosmic abyss. The implication was clear, breathtakingly so. The Milky Way, our home, is not the medium-sized spiral we had so long imagined. It is a true giant, a gravitational behemoth, and for generations, we had been measuring only a pale shadow, a mere visible facade, of its true, immense form. This discovery, this profound recalibration of our galactic address, does not simply necessitate a few numerical updates in a dusty textbook. Its ramifications are far more sweeping, far more fundamental. It compels us to completely rewrite our understanding of galactic structure, demanding a fresh, more comprehensive model that accounts for this newly revealed immensity. It drastically shifts the cosmic timeline, bringing forward the anticipated gravitational ballot and eventual collision with the Andromeda Galaxy, our nearest colossal neighbor. Moreover, and perhaps most thrillingly, it effectively doubles the sheer volume of space within our own galaxy that we must now consider in our ongoing, patient search for extraterrestrial life, expanding the cosmic canvas for potential biological existence. Every single calculation, every theoretical model, every grand narrative built upon the old, smaller size of the Milky Way now stands on shaky ground, demanding re-evaluation and revision. But perhaps the most unsettling aspect of this monumental correction, the quiet whisper that reverberates through the minds of astronomers, is the profound question it raises about our wider cosmic understanding. If we, with all our sophisticated instruments and centuries of accumulated knowledge, could get the fundamental size of our own home galaxy so spectacularly wrong, what other colossal cosmic parameters might we have similarly miscalculated? How many other galaxies, seemingly cataloged and measured with precision, might also be twice as large, or even more immense, than our current models suggest? The implications are staggering, hinting at a universe far grander, far heavier, and far more complex than our current understanding has yet dared to fully embrace. To truly grasp the immense challenge astronomers face, let us engage in a thought experiment, a mental exercise in cosmic disorientation. Picture yourself blindfolded, standing alone in the boundless, undulating expanse of the Sahara Desert. Your monumental task, your singular objective, is to accurately measure the entire desert, to chart its vast, shifting boundaries. You are forbidden from removing your blindfold, denied the luxury of sight. You cannot utilize any modern navigational aids. No GPS, no satellite imagery. Your only tools are the subtle sensations beneath your feet, the shifting grains of sand, the gentle slope of a dune, and the ceaseless whisper of the wind across your skin. How accurately, under such profoundly limiting conditions, could you hope to map such an immense, featureless landscape? This vivid analogy, though still falling short of the true cosmic scale, perfectly mirrors the formidable predicament faced by astronomers attempting to measure the Milky Way. We, as inhabitants of this colossal structure, are essentially blindfolded by our position. We reside on a comparatively minuscule rock, a planet delicately orbiting an average, unremarkable star, situated in the outer, relatively obscure reaches of one of the galaxy's sprawling spiral arms. Our direct line of sight is further hampered by immense, opaque dust clouds that effectively block our view in almost every direction, creating vast, impenetrable curtains across the galactic tableau. The very heart of our galaxy, its brilliant, enigmatic core, remains largely hidden from our direct optical gaze, shrouded behind thick, swirling walls of gas and debris. In essence, with conventional optical telescopes, we are able to perceive, at best, perhaps a mere 10% of the galaxy's true extent. The remaining 90%, the vast, unseen majority, lies concealed in the ethereal realms of infrared and radio waves, or simply vanishes into the profound, all-encompassing darkness of space. For a stark comparison, consider the relative ease with which we can measure our nearest colossal neighbor, the Andromeda Galaxy. It sits a comfortable 2.5 million light-years away from us, a magnificent, distinct spiral visible in its entirety. From our distant vantage point, we can perceive the whole thing at once, stretching majestically from edge to edge, from top to bottom. We possess the luxury of photographing its complete form, meticulously mapping its intricate spiral arms, and even precisely counting its myriad star clusters. Measuring our own galaxy, however, presents a starkly different, almost surreal challenge. It is akin to attempting to photograph your own face without the aid of a mirror, while simultaneously standing enveloped within a dense, impenetrable fog bank. The subjective, internal perspective inherently distorts and limits our ability to grasp the objective, external reality of its true form and scale. In the nascent days of astronomy, early scientists, confronted with these profound limitations, had no alternative but to employ the observational techniques available to them. They meticulously measured what they could see, patiently piecing together a rudimentary map of our galaxy through sheer perseverance and ingenuity. A key tool in their early endeavors involved tracking Cepheids variable stars, a unique class of pulsating stars whose intrinsic brightness correlates directly with their pulsation period. By observing their predictable rhythmic changes in luminosity, astronomers could accurately calculate their distances, using them as cosmic lighthouses to gauge the vast scales of space. They also painstakingly calculated the distances to globular clusters, ancient, tightly bound spherical collections of hundreds of thousands of stars, which orbit the galactic core like celestial beehives. These clusters, often found in the outer halo, provided crucial data points for mapping the three-dimensional structure of the galaxy. Piece by painstaking piece, like assembling a colossal jigsaw puzzle while wearing a blindfold, these pioneering astronomers began to construct a crude, yet foundational, understanding of our galactic home. Their methods, though limited by today's standards, laid the essential groundwork for the monumental discoveries that would follow, providing the first tentative steps in humanity's long journey to comprehend the true scale of the Milky Way. The true paradigm shift, the moment when the old assumptions began to irrevocably crumble, arrived when scientists realized they could employ motion, rather than merely light, as a primary tool for galactic measurement. This was a profound conceptual leap. The fundamental principle is elegantly simple. Everything within the galaxy, individual stars, vast swirling gas clouds, even entire star clusters, orbits the colossal, unseen center of mass. Crucially, these celestial objects move at specific, quantifiable speeds, velocities that are directly determined by the total amount of mass exerting a gravitational pull upon them. Therefore, if one could accurately measure the speed of these orbiting entities, one could, in turn, calculate the underlying mass responsible for their motion, and from that, derive an estimate of the galaxy's overall size and gravitational extent. However, it was precisely at this juncture that the observations began to deviate from the expected, revealing a truly strange and unsettling anomaly. The speeds of stars, particularly those situated at the galaxy's outermost visible edges, were observed to be moving at velocities that were far, far too fast. According to the visible mass that could be accounted for, the stars, gas, and dust that emit light, these rapidly moving peripheral stars should, by all known laws of physics, have long since flown off into the cold, empty expanse of intergalactic space, untethered from the galaxy's gravitational embrace. Yet, they stubbornly remained bound, orbiting with an inexplicable vigor. This profound discrepancy pointed inexorably to a singular, startling conclusion. Something invisible, something utterly undetectable by conventional means, was holding them in orbit. This something, this unseen gravitational scaffolding, was the enormous, ethereal halo of dark matter, a pervasive, massive, and utterly mysterious substance that wraps around the galaxy like an immense, invisible cocoon. And it was here, in this fundamental oversight, that the old measurements, the ones that confidently declared the Milky Way to be 100,000 light years across, utterly failed. They had exclusively counted what could be seen, what emitted light, the brilliant, individual stars, the glowing, incandescent gas clouds, the vibrant, luminous nebulae. In their focus on the visible, they had inadvertently, yet completely, ignored the overwhelming presence of this invisible mass, this silent, dark scaffolding that provides the vast majority of the galaxy's gravitational binding force. That, in essence, was the colossal mistake. The missing piece of the cosmic puzzle that had distorted our understanding for so long. The visible galaxy, for all its dazzling splendor, was merely a luminous veneer, a glittering facade, resting upon an infinitely vaster, unseen foundation of dark matter. The advent of modern telescopes and space-based observatories truly revolutionized our ability to peer beyond the visible and probe the hidden depths of our galaxy. The Gaia spacecraft, a marvel of celestial cartography, meticulously tracks the precise movements of over 1 billion individual stars, providing an unprecedented three-dimensional kinematic map of our galactic neighborhood. This intricate data allows astronomers to measure velocities and infer gravitational forces with extraordinary accuracy. Simultaneously, colossal radio telescopes, with their vast, dish-like apertures, are capable of mapping the faint, diffuse emissions of hydrogen gas, revealing its distribution far into the outer halo regions of the galaxy, where visible stars are scarce. Furthermore, advanced infrared instruments possess the remarkable ability to penetrate the thick, obscuring dust clouds that have historically blocked our view in visible light, unveiling hidden populations of stars and gas in previously inaccessible regions. Each of these cutting-edge technologies, each a testament to human ingenuity, reveals a different, yet complementary, layer of the Milky Way's intricate structure. Together, they paint an increasingly comprehensive picture of a galaxy far more complex and expansive than previously imagined. A particularly ingenious method employed by researchers involves utilizing satellite galaxies as cosmic test masses. The Milky Way, it turns out, is not a solitary island in space. It is surrounded by dozens of smaller, dwarf galaxies that gracefully orbit around it, much like moons circling a planet. Notable examples include the Large Magellanic Cloud and the Small Magellanic Cloud, clearly visible to the naked eye from the southern hemisphere, and the Sagittarius dwarf spheroidal galaxy, which is currently being torn apart by our galaxy's immense gravity. These satellite galaxies, in their orbital dance, are gravitationally bound to the Milky Way, and their paths are directly dictated by our galaxy's total mass, a combination of both its visible matter and its invisible dark matter. By meticulously tracking their orbits, astronomers can effectively map the true, all-encompassing gravitational field of our galaxy, revealing its full extent. When scientists painstakingly combined all this disparate, yet converging data, the precise stellar motions from Gaia, the diffuse gas maps from radio telescopes, the dust, penetrating views from infrared instruments, and the orbital mechanics of satellite galaxies, the answer that emerged was nothing short of shocking. The Milky Way, it became undeniably clear, is not the modestly sized, average spiral galaxy we had so long envisioned. Instead, it is a cosmic heavyweight, a true galactic giant. Its newly revealed width is double the old estimate, and its total mass is a staggering triple what we had previously calculated. And if the challenge of measuring our own galaxy from within proved to be so immensely difficult, what then does this imply for our attempts to measure and comprehend the vast, distant reaches of the universe, far beyond our immediate cosmic neighborhood? The implications are profound, suggesting that our entire cosmic census might require a fundamental revision. Stellar streams, though they might sound like something from a fantastical tale, are, in the stark reality of the cosmos, galactic crime scenes frozen in time. They are the silent, stretched-out remnants, the ghostly echoes of immense violence that unfolded millions, even billions of years ago. Imagine, if you will, smaller, less massive galaxies, each a delicate collection of billions of stars, innocently wandering too close to the overwhelming gravitational behemoth that is the Milky Way. Our galaxy's immense gravity, an unseen hand of cosmic power, inexorably grabs hold of these unfortunate celestial wanderers, subjecting them to unimaginable tidal forces. It slowly, relentlessly, pulls them apart, stretching their very fabric like cosmic taffy, until their organized structures are utterly annihilated. Their stars, however, do not simply vanish into nothingness. Instead, they are scattered, like glittering dust, into long, ethereal rivers of light, forming these mesmerizing stellar streams. These streams then continue to circle our galaxy, tracing intricate, elongated paths like the ribbons on an impossibly vast, unseen present. Some of these streams are truly colossal, spanning widths greater than Earth's entire orbit around the Sun. Others, remarkably, contain thousands upon thousands of stars, all moving in an eerie, perfect formation, a silent, celestial procession. For countless years, these faint, distant, and seemingly irrelevant streams were largely overlooked, dismissed as mere background noise, or perhaps as indistinct smudges in the vast cosmic tapestry. Yet, it is precisely these understated, ghostly remnants that have now emerged as the most honest, the most accurate, and the most undeniable rulers we possess for measuring the true, immense scale of our galaxy. The profound significance of stellar streams lies in a fundamental principle of physics. Their orbital paths are entirely and unequivocally determined by gravity. Every single star within one of these elongated streams moves in accordance with the total mass exerting a gravitational pull upon it. Therefore, by meticulously measuring and mapping the intricate path of a stellar stream, astronomers can, with remarkable precision, effectively measure the gravitational field of the entire galaxy. There is no guesswork involved, no speculative assumptions, no room for theoretical debate. Just the pure, unadulterated physics of gravitational interaction revealing the truth. The Sagittarius stream stands as perhaps the most famous and extensively studied example of these galactic fossil trails. It's a truly colossal structure, wrapping around the entire Milky Way multiple times, akin to an immense, shimmering ribbon encircling a grand celestial gift. Scientists, through painstaking observation and sophisticated analysis, traced this stream across the vast expanse of the sky and came to a stunning realization: it extended far, far beyond the old, established galactic boundary. The stream simply kept going and going, its stars continuing their ancient dance at immense distances, an undeniable testament to the fact that the Milky Way's gravitational influence, its unseen hand, also kept going, reaching far beyond our previous conceptions. Then came the discovery of the GD1 stream, an even more delicate, ultra-thin river of stars located deep within the outer halo. Researchers meticulously mapped its subtle curve, its gentle celestial arc, and uncovered something truly impossible, something that defied the established models. The stream bent and curved in ways that necessitated the presence of a far greater amount of mass than the visible galaxy alone could possibly contain. This left astronomers with a stark, binary choice: either the fundamental laws of physics were somehow broken in this distant corner of the galaxy, or, far more likely, we were missing something massive, something entirely invisible. The answer, as it so often is when confronted with such cosmic enigmas, was dark matter. The stellar streams, in their silent, orbital ballot, revealed the omnipresent influence of dark matter with the startling clarity of invisible ink, brought to life under an ultraviolet lamp. The immense gravitational pull that was meticulously shaping these elongated stellar rivers originated from material that we simply cannot see, material that does not emit, absorb, or reflect any form of light. This invisible substance, this pervasive dark matter, extended twice as far, perhaps even more, than the visible stars, fundamentally reshaping our understanding of the Milky Way's true dimensions. But what followed next was even stranger, pushing the boundaries of our galactic understanding to truly unprecedented scales. Scientists began to discover and map stellar streams orbiting at distances that we had previously considered to be unequivocally intergalactic space. The vast, empty voids that traditionally separate one galaxy from another. Except these regions were not empty. These newly discovered streams provided incontrovertible evidence that the Milky Way's gravitational influence, its unseen sphere of control, extended far, far farther than anyone had ever dared to imagine. Our galaxy, it became clear, does not simply terminate at the visible edge of its brilliant disk. It continues to pull, continues to claim territory, continues to exert its quiet, gravitational control over immense, previously uncharted volumes of space. The orphan stream, in particular, presents a haunting illustration of this newly revealed immensity. It orbits at such an extreme distance from the galactic center that, for years, scientists engaged in fervent debate as to whether it even legitimately belonged to the Milky Way, or if it was merely a transient visitor from some other, more distant galaxy. However, through meticulous new measurements and sophisticated kinematic analysis, its affiliation was definitively confirmed. The orphan stream is ours. This confirmation carried with it a profound implication: the Milky Way, by virtue of its gravitational dominion over this distant stream, extends at least to that immense distance, pushing the cosmic boundary of our home even farther outward. Each new discovery of a stellar stream, each meticulously mapped arc of ancient starlight, incrementally added thousands, even tens of thousands, of light years to the estimated galactic radius. Slowly, steadily, the numbers climbed 120,000 light-years, then 150,000, then an astounding 180,000. These stellar streams provided astronomers with something they had desperately needed, something that transcended theoretical models and speculative assumptions: ground truth. You can, of course, engage in academic debates about the precise location of the visible disk's edge. You can argue endlessly about where the luminous starlight truly fades into the profound darkness of intergalactic space. But you simply cannot argue with the undeniable, physical reality of a stream of stars hundreds of thousands strong, orbiting in perfect, gravitational formation. Their path, their motion is the unvarnished truth. And that truth, revealed through the patient observation of these ancient stellar rivers, consistently pushed the boundary outward, farther than was comfortable for established models, farther than could be easily explained by the old, smaller paradigms. 200,000 light-years, the stellar streams declared. The meticulous mathematics confirmed it. The direct observations corroborated it. The question, then, was no longer merely about the absolute size of the Milky Way. The more profound, more unsettling question that lingered was how, with all our accumulated knowledge and technological prowess, could we have possibly missed this colossal truth for so long? How could we have been so profoundly mistaken about the scale of our very own cosmic home? You are, at this very moment, gazing upon the Milky Way, or at least, you believe you are. What you are actually perceiving, however, is merely its skeleton, the luminous bones, the brightest and most obvious components of its magnificent structure. The profound and often unsettling truth is that an astonishing 90% of our galaxy is utterly invisible, composed of a mysterious, pervasive substance we now confidently refer to as dark matter. Dark matter is no longer a mere theoretical construct, a speculative hypothesis debated in hushed academic tones. It is a confirmed, measured, and meticulously mapped reality. We may not be able to observe it directly, to capture its elusive essence in a telescope's lens, but its gravitational effects, its profound influence on the cosmic dance, are everywhere, undeniable and overwhelmingly evident. Consider the stars at the galaxy's periphery. They orbit with speeds that are far too rapid for the visible mass alone to sustain, indicating the presence of an unseen gravitational anchor. Galaxies, in their grand, majestic spin, maintain their cohesive forms without flying catastrophically apart, a feat that would be impossible without the immense, invisible mass of dark matter providing the necessary gravitational glue. Furthermore, the very fabric of space-time, as revealed by the bending of light from distant objects around invisible mass concentrations, provides irrefutable proof of its pervasive presence. The collective evidence is, simply put, overwhelming. Within the intricate architecture of the Milky Way, dark matter does not merely contribute an extra measure of weight. It is, in fact, the fundamental architect, the silent builder of the galaxy's very structure. Imagine a colossal skyscraper where, through some strange optical illusion, you could only perceive the gleaming windows, the elegant facade, but remained utterly blind to the robust, unseen steel frame that provides its essential structural integrity. In this analogy, the myriad stars we observe are the luminous windows, while dark matter functions as the colossal, invisible frame, holding everything together, giving the galaxy its shape and its immense gravitational power. Scientists now estimate, with a high degree of confidence, that dark matter outweighs visible, normal matter by an astonishing ratio of approximately 10^1. This means that for every single star, every glowing nebula, every shimmering gas cloud you can possibly perceive, there exists 10 times more invisible mass lurking nearby, silently exerting its gravitational influence. This enigmatic material coalesces to form a massive, spherical halo that envelops the entire galaxy, diffuse and extending far beyond the bright, familiar disk of visible stars. The old measurements, in their understandable but ultimately flawed methodology, had largely ignored this pervasive dark matter halo. Their focus remained squarely on the vibrant spiral arms, the incandescent core, and the other overtly luminous features. Consequently, the galaxy appeared to be approximately 100,000 light-years across, because that was the point at which the visible stars began to noticeably thin out, where the familiar light faded into the perceived emptiness. However, the dark matter, in its silent, pervasive omnipresence, continues to extend its gravitational reach, stretching twice as far, perhaps even more, into the cosmic void. Think of it, once again, like a colossal iceberg. What you perceive above the waterline, the glistening, majestic tip, is analogous to the visible galaxy. A breathtaking, but ultimately small fraction of the whole. Below the surface, hidden from direct sight, resides a veritable mountain of ice, perhaps 10 times larger than its visible counterpart. This submerged, invisible mass is the dark matter halo. The true, comprehensive size of the Milky Way must, therefore, encompass both its luminous, visible components and its overwhelming, invisible dark matter shroud. It's an integrated entity, a magnificent whole where the unseen utterly dominates the scene. Researchers, ever ingenious in their quest to unravel cosmic mysteries, have devised clever methods to map this elusive dark matter halo, despite its inherent invisibility. One of the most powerful techniques involves gravitational lensing. Imagine, if you will, the gentle, almost imperceptible bending of light. When the light from an incredibly distant galaxy, a luminous beacon billions of light years away, embarks on its epic journey across the cosmos and happens to pass near the immense gravitational field of our own Milky Way, a subtle distortion occurs. Our galaxy's colossal dark matter halo, with its overwhelming mass, acts like an invisible, cosmic lens, slightly bending and distorting the path of that incoming light. By meticulously measuring the precise degree of this bending, this minute gravitational warp, astronomers can then calculate the exact amount of mass responsible for the distortion. The results from these gravitational lensing surveys, particularly those conducted with advanced instruments, were nothing short of astonishing. They unequivocally revealed that our dark matter halo extends out to an astounding nearly 400,000 light-years, when one carefully accounts for its faint, diffuse outer regions. This pushes the perceived boundary of our galaxy far beyond any previous estimates, confirming its colossal, unseen extent. However, even with these groundbreaking measurements, a subtle, yet persistent, debate lingers among scientists. Precisely where does one draw the line? At what point does the Milky Way definitively end, and the truly empty, vast expanse of intergalactic space truly begin? Unlike a neatly defined border on a terrestrial map, there is no abrupt, clear, cut edge to our galaxy, no cosmic fence or boundary marker. Instead, it's a gradual, almost imperceptible fading, a slow diffusion into nothingness. Is the edge where the dark matter density drops to half its central value, or perhaps a quarter, or even a mere tenth. The choice, it seems, is somewhat arbitrary, a human construct imposed upon a cosmic reality that prefers smooth transitions over sharp demarcations. There exists no universally official edge, only a slow, ethereal dissolution into the cosmic background. For practical purposes, and to allow for consistent comparisons between galaxies, astronomers often employ a concept known as the viral radius. This scientifically defined boundary marks the precise point where material, whether it be stars, gas, or dark matter, is still considered to be gravitationally bound to the galaxy. Inside this conceptual sphere, everything orbits together, held firmly within the galaxy's pervasive gravitational embrace. Outside this radius, objects are, in essence, free to drift independently through intergalactic space, no longer under the dominant gravitational sway of the Milky Way. For our galaxy, the viral radius is now estimated to sit comfortably around 200,000 to 250,000 light-years, a figure that is, notably, double the old, traditional estimate. This profound recalibration is almost entirely attributable to the overwhelming presence and extended reach of that invisible mass, the enigmatic dark matter. This revised understanding fundamentally alters how we conceptualize galactic structure. Galaxies are no longer merely perceived as isolated, luminous islands of stars floating in an otherwise empty, silent ocean of space. Instead, they are now understood to be colossal, all-encompassing halos of dark matter, within which the visible stars are merely sprinkled, like glittering dust, through their central regions. The brilliant, luminous part, the part we can actually observe with our telescopes, is, in essence, just decorative ornamentation, a beautiful but relatively minor component. The invisible part, the dark matter halo, is the true, substantial, and foundational element, the immense, unseen scaffolding that gives the galaxy its immense mass and its profound gravitational influence. And if our own galaxy possesses such an astonishing amount of hidden mass, then it logically follows that every other galaxy throughout the vast, observable universe must also be similarly endowed. The universe, in light of these revelations, has just become immeasurably heavier, far more massive than we had ever dared to truly comprehend. The Milky Way, our magnificent home, is not a solitary entity drifting alone in the cosmic ocean. It is, in fact, the dominant gravitational force within a bustling, gravitationally bound cluster of galaxies, a cosmic neighborhood teeming with dozens of smaller galaxies gracefully orbiting around us, much like a retinue of moons circling a colossal planet. We affectionately refer to these smaller companions as satellite galaxies, and their very existence, their delicate orbital dance, has irrevocably rewritten our cosmic address, fundamentally altering our understanding of our place in the universe. Among these celestial attendants, the Large Magellanic Cloud stands out as the biggest and brightest, a cloudy, ethereal smudge visible to the naked eye from the southern hemisphere. It is, in itself, a substantial galaxy containing an estimated 30 billion stars, a miniature cosmos in its own right. Nearby, its smaller sibling, the Small Magellanic Cloud, adds another 7 billion stars to this celestial tapestry. Beyond these prominent companions, we find a collection of even smaller, more diffuse entities known as dwarf galaxies: the Sagittarius Dwarf, the Draco Dwarf, the Ursa Minor Dwarf, and many more. Each one of these is a miniature galaxy, possessing its own unique collection of stars, its own ancient, unfolding history, and its own intricately defined orbital path around our larger home. For many years, scientists tended to regard these satellite galaxies as mere neighbors, distinct celestial objects that were simply passing by in the grand cosmic ballot. Their presence was noted, their movements observed, but their intrinsic connection to the Milky Way's true scale was largely underestimated. However, a quiet revolution in observational techniques, coupled with increasingly precise measurements, began to reveal a profound and undeniable truth. These celestial companions are not merely transient visitors. They are, in fact, gravitationally bound to us, inextricably trapped within the expansive sphere of the Milky Way's gravitational influence, permanent members of our cosmic family. This discovery, this redefinition of their relationship to our galaxy, changed everything. The physics behind this revelation is elegantly simple. When you meticulously measure the speed at which a satellite galaxy orbits its larger host, you can, with remarkable accuracy, calculate the total mass that is holding it firmly in place. A greater amount of mass in the host galaxy implies tighter, more energetic orbits for its satellites. Conversely, a lesser amount of mass would result in looser orbits, causing objects to gradually drift away into the vastness of space. The satellite galaxies of the Milky Way, in their precise orbital distances and velocities, provided an undeniable, direct measurement of our galaxy's total gravitational pull. Consider the Large Magellanic Cloud, situated approximately 160,000 light-years away. It completes a single orbit around the Milky Way once every 1.5 billion years. For such a massive object to remain gravitationally bound in that specific orbit at that immense distance, our galaxy must possess a truly colossal mass, far, far greater than the old estimates had ever suggested. Researchers, meticulously tracking dozens of these satellite galaxies, consistently found the same pattern. They all orbited farther out than previously expected, and they all moved at speeds greater than predicted by the old, smaller galactic models. The only plausible, unifying explanation was clear and undeniable. The Milky Way is significantly bigger and substantially heavier than we had ever truly realized. But the real breakthrough, the most compelling piece of evidence, emerged from the study of tidal streams. These cosmic phenomena occur when a satellite galaxy, in its orbital dance, ventures too close to the immense gravitational field of a larger galaxy like the Milky Way. The overwhelming tidal forces exerted by our galaxy begin to rip the smaller companion apart, pulling its stars away in long, ethereal trails of light. The Sagittarius dwarf spheroidal galaxy, as we speak, is currently undergoing this violent, destructive process, its stars stretched across the sky in a vast, shimmering stream that wraps around the entire Milky Way, a celestial testament to its slow, inexorable demise. These tidal tails, these elongated streamers of stars, function as invaluable test masses, revealing the intricate contours of our galaxy's gravitational field. They precisely show where the gravitational pull is strongest, where it gradually weakens, and, crucially, where the true gravitational boundary of the galaxy ultimately sits. By meticulously mapping a sufficient number of these tidal streams, astronomers gain an unparalleled ability to delineate the true, expansive edge of the galaxy. What scientists discovered through this painstaking work was nothing short of shocking. The streams, these ghostly remnants of devoured galaxies, extended far, far beyond the previously supposed galactic edge. Some reached out past 150,000 light-years. Others stretched to an astonishing 200,000 light-years. And a few tantalizing hints even suggested the presence of material at even greater, more extreme distances. The satellite galaxies, in their silent, orbital anguish, were undeniably screaming the truth: the Milky Way is truly colossal. This profound realization had immediate and far-reaching implications. If our galaxy is indeed this immense, then the entire concept of the local group of galaxies, our immediate cosmic neighborhood, required a fundamental redrawing. The vast, seemingly empty space between us and the Andromeda galaxy, our nearest colossal neighbor, suddenly became conceptually smaller, more densely packed. The gravitational influence of each major galaxy in the local group now extends much farther, blurring the traditional boundaries and creating a more interconnected, gravitationally intertwined system. Collisions, therefore, are likely to happen sooner. Mergers, the grand cosmic dance of galactic integration, will commence earlier than previously calculated. Every single satellite galaxy, regardless of its size or prominence, transformed from a mere celestial object into a crucial data point, every delicate orbit a precise measurement tool. Together, they painted an undeniable picture of a galactic giant, a true heavyweight, utterly unlike the medium-sized spiral we had so long imagined. And here lies the haunting, almost poetic part of this story. Some satellite galaxies orbit at such extreme distances that we are still, to this very day, in the process of discovering them. Every few years, astronomers, through diligent observation and meticulous data analysis, unearth yet another dwarf galaxy, a tiny, faint whisper of stars, hiding patiently in the vast, silent depths of the observational data. Each new discovery, each newly charted orbit, inexorably extends our galactic boundary a little farther outward. How many more are out there, patiently awaiting their revelation? How much bigger, how much more immense, does the Milky Way truly get? The answer, it seems, continues to unfold, pushing the limits of our cosmic imagination. The number, 200,000 light-years, is so staggeringly vast that it almost ceases to hold any coherent meaning for the human brain. Our minds, accustomed to terrestrial scales, struggle to process it, to visualize it, to truly grasp its immense magnitude. Let us attempt to make this colossal distance even more daunting, more profoundly humbling. Light, the fastest entity in the known universe, travels at an astonishing speed of approximately 186,000 miles per second, or about 300,000 kilometers per second. In the span of a single year, that light, traveling at its absolute, breathtaking speed limit, traverses a distance of roughly 6 trillion miles. Now, multiply that incomprehensibly vast number by 200,000. The result is that the Milky Way is approximately 1.2 quadrillion miles across, or 1.2 followed by 15 zeros. Still meaningless, isn't it? The sheer scale overwhelms our intuitive grasp of numbers. Let us try another approach, a different analogy to bring this cosmic immensity into some semblance of human understanding. If, by some miraculous means, you possessed the ability to travel at the speed of light, the absolute, unyielding speed limit of the universe, it would take you an astonishing 200,000 years to traverse the entire span of our galaxy, from one perceived edge to the other. Consider the vast sweep of human history within that time frame. When the light leaving one edge of our galaxy finally reaches the other side, the entirety of recorded human civilization, from the earliest hunter, gatherers to our current space-faring aspirations, would have risen, flourished, perhaps collapsed, and evolved again multiple times over. The journey of that light began when our distant ancestors were still living in trees, millions of years before modern humans even emerged. Put it yet another way, to truly shrink the cosmos to a more relatable scale, if our tiny planet Earth were metaphorically reduced to the size of a single grain of sand, the immense span of the Milky Way, at 200,000 light-years across, would stretch for a distance greater than that from Earth, all the way to the ringed giant of Saturn. In fact, it would stretch much, much farther than that, dwarfing the entire inner solar system. Or, to truly convey its ancient scale, consider this: the light you are hypothetically perceiving from the far edge of our galaxy, were you able to capture it, would have begun its journey long before modern humans, Homo sapiens, even existed. It would have departed before the Neanderthals roamed the earth, before Homo erectus walked upright. That light, those ancient photons, have been traveling tirelessly across the void since our most distant ancestors were still residing predominantly in the ancient forests. This scale, this profound, almost terrifying immensity, utterly breaks human intuition. We, as a species, evolved to comprehend distances on a far more modest scale. We can walk for miles, perhaps even hundreds of miles, and our brains are equipped to process and navigate such spatial relationships. But our neural wiring, our inherent cognitive architecture, never developed the capacity to truly comprehend billions of trillions of anything, let alone miles or light years. The numbers become abstract, losing their tangible connection to our lived experience. But here is where this incomprehensible size suddenly becomes profoundly personal, relevant to you, right now, today. Doubling the galaxy's perceived size doesn't just mean a larger number in a textbook, it means doubling the sheer volume of space contained within it. And volume, as you may recall from basic geometry, increases with the cube of the radius. So, if the galaxy is twice as wide, its total volume is not merely doubled, but rather, it is 8 times larger. That means 8 times more space, 8 times more stars, and, crucially, 8 times more planets. The old, familiar estimate for the number of stars in the Milky Way hovered around 200 billion. The new estimate, however, now places that number closer to a staggering 400 billion, perhaps even more. And every single one of those hundreds of billions of stars could potentially harbor its own retinue of planets. Every planet, in turn, could possess multiple moons. And every moon, tantalizingly, could conceal subsurface oceans of liquid water beneath its icy crust. The sheer number of potential homes for life The cosmic lottery tickets for biological existence has just, in one fell swoop, been doubled. Think about the profound implications of that. If life, even simple microbial life, is incredibly rare, perhaps occurring only once in a billion star systems, we have just added 200 billion more chances, 200 billion more potential cosmic laboratories for biology to emerge. If intelligent life, capable of communication and self-awareness, exists somewhere out there among the stars, we have, with this revised understanding, effectively doubled the statistical probability of either finding it, or, perhaps more intriguingly, of them finding us. However, this expanded galactic scale also carries significant implications for our long-term survival timeline as a species. The Andromeda Galaxy, our colossal galactic neighbor, is, as we speak, hurtling toward us at an impressive speed of approximately 70 miles per second (LS), around 110 kilometers per second. When galaxies collide, it's not a dramatic, fiery crash akin to two cars slamming into each other. Instead, it's a slow-motion, gravitational ballot, a majestic merger where individual stars are so incredibly far apart that direct impacts are exceedingly rare. However, the immense gravitational chaos unleashed by such an event profoundly reshapes everything within both galaxies. Scientists had previously calculated that the Andromeda collision, this grand cosmic embrace, would commence in approximately 4.5 billion years. A convenient, almost comforting distance in the future. But a bigger Milky Way means a significantly larger gravitational reach. The immense gravitational fields of both galaxies will begin to interact and pull on each other much sooner. Perhaps the initial subtle interactions, the gravitational foreplay, could begin in as little as 4 billion years, or even less. Your distant descendants, should humanity survive that long, a truly epic span of time, will witness an unimaginable transformation of the night sky. The Andromeda Galaxy will gradually grow larger, brighter, eventually filling perhaps half of the visible celestial sphere. Then, over billions of years, the two galaxies will engage in a slow, majestic dance, spiraling around each other, their elegant arms intertwining, before finally settling into one colossal, new elliptical galaxy. 200,000 light-years is not just an abstract number, it is, profoundly, your future. It is your past, the immense stage upon which every single human story ever told has played out, confined to one tiny, ephemeral corner. And we have just realized that this stage is, in fact, twice as vast, twice as magnificent, as we had ever dared to imagine. The impending collision with the Andromeda Galaxy is not a mere theory, a speculative possibility floating in the realm of academic conjecture. It is a confirmed, undeniable fact, established through decades of meticulous observation and precise calculation. Our colossal neighboring galaxy is, at this very moment, racing toward us at a breathtaking speed of 70 miles per second, or roughly 110 kilometers per second. This cosmic encounter, this grand gravitational embrace, is utterly inevitable. For generations, scientists diligently calculated that this monumental impact would commence in approximately 4.5 billion years. A timeline that, while immense, offered a certain comfort in its distant futurity. You could, hypothetically, mark your calendars for that far-off date. However, those calculations, those meticulously derived timelines, were predicated upon the old, smaller estimates for the sizes of both galaxies. A smaller Milky Way, it was assumed, possessed a more confined gravitational reach, implying a greater effective distance, a larger buffer of empty space, between us and Andromeda. But a bigger Milky Way fundamentally alters this intricate cosmic equation. With a significantly increased mass and a vastly expanded gravitational influence, our galaxy's gravitational reach extends much, much farther. Consequently, the two colossal galaxies will begin to pull on each other, to exert their mutual gravitational sway far sooner than previously predicted. Their immense dark matter halos, those invisible, pervasive envelopes of mysterious mass that stretch for hundreds of thousands of light years outward, will be the first components to interact. When these ethereal halos touch, when these two invisible giants begin to interpenetrate and mingle, the gravitational dance, the initial stages of the collision, truly begin. Think of it conceptually like two individuals walking toward each other across a vast plain. If both individuals are, in reality, far larger and possess a greater physical presence than you initially assumed, they will inevitably bump into each other, make contact, much sooner than your initial predictions suggested. The same fundamental principle applies, albeit on a truly galactic scale, with the immense gravitational fields replacing the physical bodies. New, more sophisticated models, incorporating the revised galactic sizes, now suggest that the initial gravitational interaction, the delicate prelude to the full collision, could commence in under 4 billion years, perhaps even as early as 3.5 billion years from now. The precise timeline remains an active area of research, dependent on even more precise measurements that astronomers are still painstakingly collecting. However, the overarching trend is undeniably clear. Bigger galaxies inherently mean earlier contact, a more rapid onset of this cosmic event. So, what exactly happens during a galactic collision of this immense magnitude? Let's trace the cosmic drama as it unfolds. The first stage, as mentioned, involves the merging of the outer dark matter halos. These colossal, invisible envelopes begin to interpenetrate, their constituent dark matter particles passing through each other like silent, non-interacting ghosts. While there are no physical collisions at this stage, no dramatic impacts, the gravitational forces are intensely real. Stars within the outer regions of both galaxies begin to feel the complex, conflicting pulls from two distinct galactic centers. Their long, stable orbits become destabilized, perturbed by these new, powerful gravitational influences. Some stars, receiving sudden, energetic kicks, might be flung violently into the cold, empty expanse of intergalactic space, ejected forever from their galactic homes. Others, conversely, might plunge inward, drawn toward the burgeoning, chaotic cores. Next, the outer stellar halos, the diffuse regions of scattered stars beyond the main disk, begin to interact. These stars are already moving at high velocities, barely held within their respective galaxies' gravitational wells. As the other massive galaxy approaches, the delicate balance is disturbed. More stars are flung into intergalactic space, irrevocably lost. But, conversely, some stars from one galaxy might get gravitationally captured by the other, effectively stolen in this grand cosmic exchange. The galaxies, in essence, begin to trade stars like trading cards in a cosmic game. Then come the powerful tidal forces. As the galaxies make their initial passes through each other, the gravitational pull exerted by each galaxy is stronger on the closer side of the other galaxy than on its farther side. This differential gravitational force creates immense stretching, literally pulling both galaxies apart. Material, both stars and gas, gets drawn out into incredibly long, ethereal streamers known as tidal tails. These magnificent, destructive tails can extend for millions of light years into space. Beautiful yet stark proof of the titanic gravitational forces at play, remnants of where cosmic giants once fought. Finally, the visible stellar disks, the familiar, luminous spirals we recognize, begin to collide. But again, it's not a catastrophic crash. It's more akin to two immense, ethereal clouds slowly passing through each other. Individual stars are so incredibly far apart that direct impacts between them are astonishingly rare. You could comfortably fit millions of Earths between neighboring stars. However, the gravitational chaos, the immense perturbation of orbits, is undeniably real. A remarkable phenomenon occurs during this phase. The vast gas clouds within both galaxies are compressed. This compression, in turn, triggers a furious burst of star formation. Millions upon millions of new stars ignite across both galaxies, transforming them into starburst galaxies, a breathtaking cosmic fireworks display, a testament to the creative power of destruction. The Milky Way and Andromeda will not simply merge in a single pass. Instead, they will orbit each other multiple times, engaging in a complex, gravitational dance, spiraling inward over billions of years. Each pass will strip away more material, each gravitational embrace will drive their central cores closer together. Tidal forces will relentlessly shred the elegant spiral arms, scattering stellar streams in every conceivable direction. The once organized, beautiful structures will become warped, distorted, and eventually utterly unrecognizable. Eventually, perhaps a billion years after their initial gravitational contact, the galaxies will fully merge, settling into a new, stable configuration. The ultimate result will be a massive, sprawling elliptical galaxy, devoid of the elegant spiral arms and the organized disk structure. Instead, it will be a vast, luminous blob composed of trillions of stars, all orbiting in random, chaotic directions. Astronomers have already, with a touch of cosmic whimsy, given this future merged galaxy a name, Milkomeda, a rather cute moniker for the eventual demise and rebirth of two ancient, magnificent spirals. But here arises a critical, deeply personal question: will Earth survive this cosmic cataclysm? Will our Sun endure? And, perhaps most poignantly, will humanity still be around to witness this awe-inspiring spectacle? The good news: first, our Sun will, in all likelihood, survive the merger. It is situated far enough from the tumultuous galactic center that it will probably avoid the most violent, disruptive regions of the collision. Earth, our precious blue marble, might be flung into a dramatically different orbit around the newly formed galactic core, or perhaps even ejected entirely into the cold, isolating expanse of intergalactic space. Alternatively, it might by sheer cosmic chance remain roughly where it is, albeit in a vastly altered gravitational environment. The odds, fortunately, favor the survival of our solar system as a cohesive unit. Now for the less comforting news: the Sun, our life-giving star, will be long dead by then. Our star has an estimated 5 billion years of nuclear fuel remaining in its core. The Andromeda collision, as we've discussed, is now expected to commence before the Sun finally exhausts its hydrogen and evolves into a red giant, eventually shrinking to a white dwarf. So, while the Sun will likely survive the merger, its habitable lifetime will be drawing to a close. However, there's a fascinating twist: we might, just might, get a front row seat to the early stages of this cosmic drama. A bigger Milky Way, as we now understand, has moved up that timeline. The grand show, the initial gravitational interactions, will begin sooner, offering a potential spectacle for any surviving civilizations. And here is the part that few openly discuss: the unsettling layer of uncertainty that adds further intrigue to this cosmic narrative. What if Andromeda, our colossal approaching neighbor, is also significantly bigger than our current measurements suggest? Our estimates for its size and mass, based on similar observational techniques to our own galaxy, could also be profoundly mistaken. If both galaxies are, in reality, even larger and more massive than our revised estimates, the collision will happen even sooner. The gravitational chaos unleashed will be even more intense, and the final merged galaxy, Milkomeda, will become an even more colossal, truly massive elliptical behemoth. We are, in fact, already detecting the subtle, nascent signs of this impending encounter. Andromeda's dark matter halo, that invisible, pervasive envelope of mass, already extends toward us. Our own dark matter halo reaches out toward it. It is entirely plausible, in fact, increasingly likely, that these two immense, invisible halos might already be gently touching, subtly interpenetrating. The collision, in its most preliminary, invisible form, might have already begun, slowly, imperceptibly, in the dark matter that envelops both galaxies. 4 billion years sounds like an eternity to the human mind, an incomprehensibly vast span of time. But on cosmic timescales it is, quite literally, tomorrow. And tomorrow, with these new revelations, just got a little closer, a little more imminent. Everything, in the grand cosmic scheme, ultimately comes down to mass. The Milky Way, our home galaxy, has just undergone a truly monumental weight gain, a colossal increase in its estimated mass. Trillions upon trillions of solar masses, previously unaccounted for, have now appeared in the meticulous calculations derived from new observational data. The old, long-held estimates suggested that our galaxy contained approximately 1.5 trillion times the mass of our Sun. A significant portion of that was already attributed to dark matter, the invisible glue holding it all together. However, the new, refined measurements now point to a staggering 4 trillion solar masses, perhaps even more. We have, in less than a decade, effectively tripled the estimated mass of our galaxy. To fully grasp what a solar mass truly represents, consider our own Sun. It weighs an unfathomable 2 billion kilograms, a number so astronomically large it almost instantly transforms into an abstract concept devoid of tangible meaning. That colossal weight is defined as one solar mass. For perspective, our Earth, the very ground beneath your feet, weighs a staggering 300,000 times less than the Sun. Even Jupiter, the gas giant that utterly dwarfs all other planets in our solar system, weighs 1,000 times less than the Sun. Indeed, if you were to meticulously sum the mass of every single object in our solar system, all the planets, moons, asteroids, and comets, excluding only the Sun itself, their combined weight would barely amount to a mere 1% of one solar mass. Now, take that colossal mass of our Sun and multiply it by 4 trillion. That, in essence, is the Milky Way, a true gravitational giant, a cosmic heavyweight beyond our prior comprehension. So, where did all this immense, extra mass originate? Did the galaxy suddenly and inexplicably gain weight? Did material spontaneously appear from nothingness, defying the fundamental laws of conservation? Obviously not. This immense mass was always there, an omnipresent, invisible component of our galaxy. We simply lacked the sophisticated tools and methodologies to measure it accurately, to truly quantify its pervasive influence. The vast majority of this newly accounted for mass is, as you might suspect, dark matter, invisible, utterly undetectable by direct means, except through its undeniable gravitational effects. The old measurements, in their inherent limitations, primarily focused on the visible stars and gas. They attempted to estimate the amount of dark matter indirectly, largely by analyzing galactic rotation curves. The principle was straightforward. Stars orbit the galactic center at speeds that are directly determined by the total mass enclosed within their orbit. By measuring these orbital speeds, astronomers could then, theoretically, calculate the underlying mass. However, these measurements predominantly sampled only the inner regions of the galaxy, the areas where visible stars are abundant and observations are relatively straightforward. The vast, unseen outer halo, the region where dark matter truly dominates, remained largely unquantified, its mass significantly underestimated. That, precisely, was the profound mistake. New, groundbreaking techniques have utterly transformed this game of cosmic measurement. The precise orbits of satellite galaxies, those smaller companions circling our own, provided direct measurements of the galaxy's total mass at truly immense distances, far beyond the visible disk. Stellar streams, those ghostly ribbons of stars torn from devoured galaxies, meticulously mapped the intricate gravitational field in the galaxy's outermost regions. Furthermore, sophisticated computer simulations, comparing our galaxy's observed properties to thousands of virtual galaxies with known masses and dark matter distributions, provided crucial corroboration. All these diverse methods, converging from different observational and theoretical pathways, consistently agreed the Milky Way commands a staggering 4 trillion solar masses. Our galaxy is unequivocally a cosmic heavyweight. This profound increase in our galaxy's estimated mass carries enormous implications. More mass inherently means stronger gravity. Stronger gravity, in turn, means that the Milky Way can hold a greater number of satellite galaxies firmly in orbit, preventing them from drifting away. It also means we can more easily strip stars and gas from passing neighbors, literally cannibalizing smaller galaxies that venture too close. We now understand that the Milky Way dominates the local group, our immediate galactic neighborhood, far more completely than previously thought. Andromeda, our colossal neighbor, was traditionally regarded as the undisputed bigger sibling, the alpha galaxy in our local cluster. However, these new measurements suggest that we might be equals in terms of mass, or perhaps, tantalizingly, even slightly larger. The Milky Way and Andromeda, it now appears, weigh roughly the same, each commanding approximately 4 trillion solar masses. Two galactic superpowers on an inevitable collision course. More mass also fundamentally rewrites our understanding of how the Milky Way formed and evolved. Galaxies, it is now understood, grow not merely by gently accumulating diffuse gas and dust, but by violently consuming smaller galaxies. The larger a galaxy becomes, the more it has, by definition, consumed. A galaxy boasting 4 trillion solar masses possesses a truly bloody and cannibalistic history. We have devoured hundreds of dwarf galaxies, perhaps even thousands, over our long cosmic lifespan. Every elongated stellar stream observed in the halo is a silent, shimmering testament to a past meal, a smaller galaxy that ventured too close and paid the ultimate price. The Sagittarius dwarf spheroidal galaxy, as mentioned, is currently being actively consumed, torn apart, and digested by the Milky Way. Its stars are slowly scattering across our galaxy's disk and halo. In a few 100 million years, virtually no visible trace of it will remain, save for ghostly echoes buried deep within the astronomical data. This, fundamentally, is how galaxies grow, through a process of galactic cannibalism, a brutal, yet essential, form of cosmic empire building. But here lies the truly terrifying, almost surreal part of this revelation. If our galaxy is indeed 4 trillion solar masses, and the overwhelming majority of that mass is composed of invisible dark matter, it means we reside within a galaxy that is, by volume and mass, predominantly made of something we cannot see, cannot touch, and cannot directly detect. A staggering 90% of everything that gravitationally surrounds us is composed of this enigmatic, unseen material. You might believe you comprehend where you live, that you understand your cosmic neighborhood. But the truth is far more profound and unsettling. You are, at this very moment, swimming through an immense, pervasive ocean of dark matter, and you cannot, in any tangible way, feel the water. 4 trillion solar masses, primarily composed of invisible material. That is home. That is the Milky Way. And we have only just begun to truly grasp how enormous, how overwhelmingly substantial it truly is. The galaxy, it turns out, does not cease to exist where the visible stars gradually thin out. It continues its immense, unseen presence, stretching far beyond anything discernible to our optical instruments, extending deep into the mysterious realm of pure dark matter. Scientists refer to this colossal, invisible structure as the dark matter halo. It is a massive, spherical cloud, composed entirely of these elusive, invisible particles, silently enveloping the entirety of the visible galaxy, like an immense, ethereal shroud. This dark matter halo is not a minor, incidental feature. It is, in fact, the dominant structural component, the very foundation, the colossal gravitational cage that meticulously holds everything together. Conservative estimates, based on meticulous modeling and observation, place the radius of this halo at a staggering 250,000 light-years. This marks the viral radius, the theoretical boundary where material is still considered to be gravitationally bound to the galaxy. However, some more expansive models suggest that the halo extends far, far farther than even this impressive figure, to 400,000 light-years, perhaps even 600,000. Some highly advanced calculations, pushing the boundaries of current understanding, even suggest it might stretch past a staggering 1 million light-years. Imagine, for a moment, the sheer, mind-boggling scale of 1 million light-years. If this more extreme estimate for our dark matter halo proves true, it would render the Milky Way approximately 20 times wider than the old, traditional textbook measurements. That's 20 times more space under our direct gravitational control, an empire of unseen mass. Now, picture the Andromeda Galaxy, our nearest colossal neighbor, which resides approximately 2.5 million light-years away. If our dark matter halo indeed reaches 1 million light-years outward, and Andromeda's halo extends a similar distance, then a mere 500,000 light-years of truly empty space would separate us. This implies that the halos, these two invisible clouds of dark matter, might already be gently touching, subtly interpenetrating, mixing their unseen particles in a silent, cosmic prelude to the eventual, full-scale collision. We cannot, by definition, see the dark matter halo directly. Dark matter, by its very nature, does not emit light, nor does it absorb it. It does not reflect light, nor does it interact in any way with electromagnetic radiation, the very medium through which we perceive the universe. It interacts solely through gravity, its immense mass exerting a powerful, undeniable pull on everything around it. But that gravity, that unseen force, is undeniably real, meticulously measurable, and overwhelmingly powerful. Researchers meticulously map the halo using a combination of indirect methods, each offering a unique window into its invisible structure. The precise orbits of satellite galaxies, those smaller companions circling our own, reveal where concentrations of mass are located, allowing astronomers to infer the distribution of the dark matter. Gravitational lensing, as we discussed earlier, shows where the fabric of space-time itself is subtly curved by the halo's immense mass. Furthermore, sophisticated computer simulations predict how dark matter should distribute itself throughout a galaxy, based on our best current theories of galaxy formation. All these diverse lines of evidence consistently point to the same underlying structure, a massive, spherical halo, dense near the galactic center, but gradually thinning out, becoming more diffuse, as it extends toward the outer edges. There is no sharp boundary, no sudden termination, just a slow, ethereal fade into the vastness of intergalactic space. The existence of this colossal dark matter halo provides elegant explanations for many long-standing cosmic mysteries. Why, for instance, do stars at the galaxy's extreme edges orbit so rapidly, defying the gravitational pull of the visible matter alone? The halo's immense, unseen gravity holds them firmly in place. Why do galaxies, in their majestic, rapid spin, not simply fly apart, their constituent stars flung into the void? The halo provides the crucial, extra mass necessary for their cohesion. Why do we observe more gravitational lensing than can be accounted for by visible matter alone? The halo, with its pervasive, unseen mass, bends space-time, providing the missing gravitational source. But here is what makes this revelation truly strange, profoundly personal, and almost unsettling. You are, at this very moment, unequivocally inside this dark matter halo. Dark matter, in its elusive omnipresence, surrounds you, passes through you, permeates the very space you occupy. Earth, our home planet, is ceaselessly swimming through an immense sea of dark matter particles, moving at hundreds of miles per second as our solar system orbits the galactic center. Trillions upon trillions of these ethereal particles stream through your body every single second, passing through your atoms as if they were not even there. And yet, you feel absolutely nothing. They interact with normal matter so incredibly weakly, so rarely, that they pass through us like ghosts, leaving no discernible trace. Scientists are, of course, actively trying to detect dark matter directly, to finally capture one of these elusive particles and understand its fundamental nature. Deep underground laboratories, shielded from cosmic rays and terrestrial interference by thousands of feet of rock, house incredibly sensitive detectors, patiently waiting for the incredibly rare event of a dark matter particle colliding and bouncing off a normal atom. So far, despite decades of dedicated effort and increasingly sophisticated technology, nothing conclusive has been detected. The particles are either too shy, too incredibly rare in their interactions, or perhaps we are simply looking in the wrong way, employing the wrong techniques to coax them from their invisible hiding places. If the dark matter halo truly extends to 1,000,000 light-years, as some of the more expansive models suggest, then the Milky Way effectively claims an enormous, truly staggering volume of space as its gravitational dominion. Most of the local group, our immediate cluster of galaxies, would then fall squarely within our galaxy's sphere of influence. This means we are not merely a single, isolated galaxy in the vast cosmic ocean. We are, in essence, a galactic empire, a colossal superstructure of invisible mass dominating and shaping everything around us. And if our halo is indeed this immense, then it stands to reason that every other galaxy in the universe also possesses a similarly vast and pervasive dark matter halo. This profound realization fundamentally alters our perception of the universe itself. The cosmos is not, as we once simplistically imagined, mostly empty space dotted with isolated, luminous galaxies. Instead, the universe is predominantly composed of these immense dark matter halos, with galaxies merely embedded within their centers like tiny, glittering seeds within colossal, ethereal fruits. Everything we can visually perceive, every star, every nebula, every glowing galaxy, represents only a minuscule fraction of what truly exists. The visible universe, in this new light, is merely an intricate, beautiful decoration, a luminous embellishment upon an infinitely vaster, invisible scaffold of dark matter. 1,000,000 light-years of pervasive, unseen darkness. That is the Milky Way. That is home. And we are only just beginning to truly grasp the monumental, overwhelming enormity of it all. The galaxy is spinning at an astonishing rate, far too rapidly, in fact, for its visible components to remain gravitationally bound. It should, by all conventional laws of physics, be flying apart, its stars flung into the cold, isolating expanse of intergalactic space. Stars situated at the outermost edges of the galaxy orbit at speeds that, quite frankly, make no logical sense based solely on the visible mass. They should, according to Kepler's elegant laws of motion, slow down considerably as their distance from the galactic center increases, much like planets in our solar system. Yet, they stubbornly refuse to conform to this expectation. And to this very day, nobody fully comprehends precisely why. Herein lies the core of the problem, the profound cosmic puzzle that has puzzled astronomers for decades. In our own solar system, the principle is clear and demonstrably true. Planets farther from the Sun orbit at significantly slower speeds. Mercury, the innermost planet, races around its star in a mere 88 Earth days. Earth, our home, takes 365 days. Neptune, the distant ice giant, completes a single, leisurely orbit in a staggering 165 years. The farther out you go, the weaker the Sun's gravitational pull becomes, and consequently, the slower the orbital velocity of the planet. This is a fundamental tenet of basic physics, a principle meticulously worked out by Isaac Newton over 3 centuries ago. Logically, galaxies should operate under the same fundamental principles. The vast majority of a galaxy's visible mass, its luminous stars and gas, is concentrated near its central regions. Therefore, stars located farther out, experiencing a weaker gravitational force, from this central concentration, should exhibit slower orbital speeds. When one measures their velocities, one would intuitively expect to see a smooth, predictable curve, gradually decreasing with increasing distance from the center. Except, that is precisely not what happens. Instead, stars at the extreme edges of the galaxy orbit at velocities that are remarkably similar, almost identical, to the speeds of stars much closer to the galactic core. The galactic rotation curve, when plotted, stubbornly remains flat, defying the expected decline. This observed phenomenon is, by all accounts of visible matter, utterly impossible, unless, of course, there is a substantial amount of additional mass present, lurking out there beyond the reach of our visible telescopes. This unseen additional mass is, inevitably, dark matter. Always dark matter. The invisible halo, with its pervasive and immense gravitational influence, provides the crucial extra mass necessary to keep these outer objects moving at their inexplicably high speeds. The flat rotation curve, this persistent anomaly, serves as the definitive smoking gun, the irrefutable proof that dark matter exists in truly enormous quantities, far out in the galactic periphery. But here is where the situation becomes even stranger, more complex, and more profoundly puzzling. Even when meticulously accounting for the inferred presence and gravitational pull of dark matter, the observed speeds of some stars in the outermost regions remain higher than even the revised predictions. Some stars in the extreme outer halo are observed to be moving at velocities of 130 miles per second, 210 kilometers per second. Others hit 150 miles per second, 240 kilometers per second. These velocities are perilously close to the escape velocity for that region of the galaxy. The stars are, in essence, almost fast enough to completely leave the galaxy, to break free from its gravitational embrace and drift into the lonely expanse of intergalactic space. Why do they orbit so incredibly close to the very edge of escape? What delicate, fine, tuned mechanism keeps them just barely bound, perpetually skating on the precipice of freedom? This is known as the escape velocity problem, and it continues to haunt and perplex astronomers. One plausible possibility is that our current models still underestimate the galaxy's total mass. Perhaps there is even more dark matter present than current theoretical models suggest, a greater density or extent of the invisible halo than we have yet been able to accurately quantify. Maybe the dark matter halo is, in fact, denser at its extreme edges than we currently believe, or perhaps our mass calculations, even with the recent revisions, are still somewhat incomplete. Another intriguing possibility suggests that the galaxy might have recently undergone a period of rapid growth. If the Milky Way devoured a particularly large dwarf galaxy within the last few billion years, the immense energy released during such a merger could have injected a population of stars into these unusually fast orbits. These stars, being relatively recent additions, might not yet have had sufficient time to settle into stable, lower, energy paths. They would still retain the immense kinetic energy imparted by the collision, appearing as rapidly moving, barely bound objects. Evidence, in fact, supports this idea. The Sagittarius dwarf spheroidal galaxy, as we've discussed, is currently in the process of being torn apart by the Milky Way's gravity, and its stars are indeed scattering into our galaxy's halo at high speeds. In a billion years, these newly introduced stars will appear indistinguishable from other native halo stars. Fast, ancient, and ultimately, mysterious in their origin. But we, in this cosmic snapshot, are witnessing this process in action. But what follows next in this cosmic enigma is even stranger still. While many stars are observed to be moving too fast, some stars, counterintuitively, appear to be moving too slowly. These are, in a sense, hypervelocity stars. In reverse, objects that, based on their location and the visible mass, should be orbiting at much higher speeds. But instead, they drift along almost sluggishly, as if trapped in a viscous, cosmic molasses. For these peculiar, slow outliers, astronomers currently lack a good, comprehensive explanation. The galactic rotation curve, in its theoretical purity, should be a relatively simple affair: measure the speeds of stars, calculate the enclosed mass, and everything should fit neatly into place. Instead, every new, more precise measurement reveals additional anomalies, more puzzling outliers, more stars stubbornly doing things that, according to our current understanding, they should not be able to do. This is precisely where dark matter theories are rigorously tested and refined. Different models of dark matter, such as warm dark matter, cold dark matter, or self-interacting dark matter, predict subtly different rotation curves, different distributions of mass, and different behaviors in galactic cores. So far, the cold dark matter model, which posits that dark matter particles are slow, moving and non-interacting, provides the best fit for the observed data. However, the fit is not perfect. Small discrepancies, nagging inconsistencies persist. These minute deviations might, tantalizingly, point toward entirely new physics, a deeper, more profound understanding of the universe. Or, they might simply be attributable to subtle measurement errors that will eventually be resolved with even greater precision. The galaxy spins faster than our visible models predict. Stars orbit at speeds that defy simple, straightforward explanations. And the newly revealed, larger galactic size only exacerbates this problem. A greater volume, a larger number of stars, means an even greater multitude of peculiar velocities and puzzling orbital dynamics that demand comprehensive explanation. Physics, as we understand it, works remarkably well everywhere else in the universe. It accurately describes the intricate dance of planets and solar systems, the gravitational cohesion of dense star clusters, and the grand movements of distant galaxies. But in our very own cosmic backyard, within the intricate and often perplexing rotation curve of the Milky Way, something is still not quite adding up, urging us to continue our patient quest for deeper understanding. The Milky Way, our home galaxy, has, for decades, been confidently depicted as possessing 4 major spiral arms. These were traditionally identified as the Scutum, Centaurus arm, the Norma arm, the Sagittarius arm, the Perseus arm, and sometimes the Cygnus arm. Each of these arms was envisioned as a majestic river of stars, vast clouds of gas, and obscuring dust, all gracefully spiraling outward from the galaxy's luminous, enigmatic center. These arms, being regions of enhanced density and prolific star formation, are particularly bright and relatively easy to spot, standing out vividly against the darker background of inter-arm space. They were, in essence, the prominent highways of our galaxy where new stellar life was constantly being forged. However, as technological prowess advanced, bringing forth an array of better, more sensitive telescopes, our view of these familiar structures began to shift. Infrared instruments, with their remarkable ability to peer through the thick, opaque dust clouds that obscure visible light, started to reveal previously hidden features. Radio telescopes, designed to map the faint emissions of hydrogen gas, provided an entirely different perspective, tracing the distribution of gas across vast galactic scales. Space-based observatories, positioned above the distorting veil of Earth's atmosphere, offered unprecedented clarity and resolution. Each new tool, each fresh observational technique, consistently revealed features and structures that we had, for so long, entirely missed. The FAR 3 kiloparsec arm was one of the first revelations, a significant, albeit minor, spiral arm patiently hiding behind the brilliant glare of the galactic core. We simply couldn't see it with optical telescopes because the dense, luminous center of the galaxy effectively blocked our view. But infrared instruments, with their dust-penetrating capabilities, cut through the obscuring material, and there it was, an entire arm, thousands of light years long, existing right under our noses, previously unknown. Then came tantalizing hints of other, more complex structures. The local arm, the very spur within which our own solar system resides, was long considered a minor, insignificant branch of a larger arm. However, new, more comprehensive observations now suggest that it might actually be a major arm in its own right, connecting to even larger, more extensive structures farther out. What we once thought was merely a small, peripheral branch might in fact be a whole, significant limb of the galaxy. The outer arm posed yet another profound mystery. Situated at the extreme, diffuse edge of the visible galaxy, some researchers initially dismissed it as merely a scattering of isolated stars, lacking any cohesive structure. Yet, detailed mapping, utilizing advanced observational techniques, revealed organized, coherent spiral patterns extending far into these previously thought to be empty outer regions. The galaxy, it became clear, possessed intricate structure and organization in areas where we had long assumed there was only emptiness and diffuse, scattered starlight. But here is the truly bizarre and enduring puzzle that confounds astronomers. Nobody, despite decades of intense research and sophisticated modeling, definitively knows how spiral arms truly form and maintain their elegant structures. We observe them in almost every disk galaxy across the universe. Beautiful, graceful spirals that define the very aesthetic of galactic form. Yet, the underlying physics responsible for their persistence remains remarkably murky and incompletely understood. Here's the fundamental problems. Stars within a galaxy orbit the galactic center at different speeds. Inner stars, closer to the dense core, orbit much faster. Outer stars, farther away, orbit significantly slower. If spiral arms were simply fixed concentrations of stars, they would, over time, inevitably wind tighter and tighter, like stirring cream into a cup of coffee. Within just a few galactic rotations, these arms should, theoretically, blur and dissipate into a smooth, featureless disk. Yet, they do not. Spiral arms demonstrably persist for billions of years, maintaining their distinct patterns. This persistent stability strongly suggests that they are not rigidly fixed material structures. Instead, the prevailing theory posits that spiral arms are density waves, regions where stars, gas, and dust temporarily bunch up, creating the illusion of a fixed arm. Imagine a traffic jam on a highway. The individual cars move through the jam, but the jam itself, the region of congestion, remains relatively stationary. Similarly, stars and gas clouds move into and out of these density waves, experiencing temporary compression and enhanced gravitational pull, which then triggers new star formation, making the arms appear bright. The density wave theory works remarkably well mathematically, providing a compelling explanation for the longevity of spiral arms. However, observational data continues to find subtle exceptions and inconsistencies. Some arms, for instance, exhibit an unexpectedly high concentration of very young, massive stars, which is not entirely consistent with the density wave model alone. Others show curious gaps or irregularities where stars should be. The outer arm, in particular, appears too massive and structurally robust to be merely a transient wave. It might represent a more enduring, material structure, perhaps material pulled out during a past galactic collision millions of years ago. The newly revealed, larger size of the Milky Way further complicates this already intricate puzzle. More space inherently means more room for structure to develop and extend. Spiral arms can stretch farther, encompassing greater volumes of space. New, previously undiscovered arms could potentially form in regions we once thought were entirely empty. The spiral pattern, far from being a simple, elegant design, becomes a much more complex, potentially chaotic, and dynamic phenomenon. Recent, incredibly precise surveys conducted by the Gaia spacecraft, which has mapped the positions and motions of over 1 billion stars with unprecedented accuracy, have added another layer of complexity. The Gaia data has revealed intricate substructure within the spiral arms themselves, branches, spurs, and even subtle gaps. The overall spiral pattern, it seems, is not clean and smoothly defined. Rather, it is messy, somewhat chaotic, almost akin to the intricate, irregular branching patterns of an ancient tree, growing in myriad directions. Some researchers, based on this new wealth of data, now argue that the Milky Way is not, in fact, a grand design spiral galaxy, a galaxy with prominent, well-defined and continuous spiral arms. Instead, they suggest it might be a flocculent spiral, a galaxy characterized by patchy, irregular, and poorly defined arms, more like a collection of short, fragmented segments. This classification would help explain why different surveys, using different observational techniques and focusing on different tracers, stars, gas, dust, consistently find varying numbers of spiral arms. Everyone, in essence, is seeing different features, depending on what they are measuring and how they are looking. The debate, as is often the case in cutting-edge science, continues with vigor. More powerful telescopes, more precise data, and more impassioned arguments at international conferences will undoubtedly refine our understanding. But one thing is now abundantly clear. The Milky Way is far more complex, far more intricate than the simple four-arm diagram that once graced the pages of our astronomy textbooks. Hidden structures, entire arms that we missed for decades, fill the galaxy. And if we manage to overlook entire spiral arms in our very own galaxy, what other grand features, what other magnificent structures might still be hiding in the pervasive darkness, patiently awaiting the right instrument, the right perspective, to finally reveal them to our astonished gaze, drawing a precise line, a definitive boundary, to mark the exact edge of a galaxy sounds deceptively simple. In reality, it is, in a profound sense, impossible. Galaxies, unlike countries or continents on a terrestrial map, do not possess neat, clearly defined boundaries. There is no cosmic border wall, no luminous sign proclaiming, "Now leaving the Milky Way." Instead, the density of stars and gas simply thins out gradually, slowly, imperceptibly, until there are very few left, or perhaps only a scattering of isolated, lone stragglers adrift in the vast emptiness. At what precise point, then, does that gradual thinning transition into? Not the galaxy. This is not merely a philosophical question, an abstract point of academic debate. It is a very real, practical problem for astronomers. Scientists require a consistent definition, a standardized measurement, a universally agreed upon method to compare galaxies across the cosmos. But nature, in its boundless complexity, rarely cooperates with our human need for clean, unambiguous categories. The universe, it seems, cares little for our desire for crisp lines and definitive borders. Consequently, several definitions for a galaxy's edge exist, each serving a different purpose, and none of them, in isolation, are truly perfect or all-encompassing. The optical radius, for instance, marks the point where visible stars become too faint to easily detect. This definition effectively delineates the bright, luminous disk of the galaxy, the most obvious and easily observed part. For the Milky Way, this would yield the old, familiar estimate of roughly 100,000 light-years. However, this definition critically ignores all the faint, dim stars, the countless red dwarfs, the scattered halo objects, the diffuse stellar populations that extend far beyond the bright disk. It's akin to attempting to measure the size of a sprawling city by counting only its tallest skyscrapers and completely disregarding the vast network of houses, parks, and suburban sprawl that constitutes its true extent. The viral radius, as we've discussed, offers a more scientifically robust definition. It marks the boundary where objects are still considered to be gravitationally bound to the galaxy. Inside this conceptual sphere, all stars, gas, and dark matter orbit cohesively around the galactic center. Outside this radius, Objects are, in principle, free to drift independently through intergalactic space. For the Milky Way, this yields a significantly larger estimate of approximately 250,000 light-years. This is a much better, more comprehensive measure, reflecting the true gravitational dominion of the galaxy. Yet, even this definition presents certain ambiguities. Some stars, for example, are found just outside the viral radius, but still share the overall motion of the galaxy through space. They formed here. They are part of our galaxy's history. Are they still technically part of the galaxy or not? The viral radius, strictly speaking, says no. Common sense, however, might suggest a more nuanced, maybe. And then there is the pervasive dark matter halo, which extends far, far beyond everything else. If this halo reaches an astonishing 1 million light-years outward, as some models propose, is Garth at the real edge of the galaxy? Most astronomers would likely argue no. The halo fades so incredibly gradually, its density dropping so imperceptibly, that choosing any specific boundary point becomes inherently arbitrary. It's much like trying to definitively mark where Earth's atmosphere ends. Technically, atmospheric particles extend thousands of miles into space. Practically, for all intents and purposes, it's considered to be gone after about 100 miles altitude. So, where do you draw the line? The choice is subjective, driven by the specific context and purpose of the definition. The situation becomes even more complex when we consider galactic winds. The Milky Way, through the violent explosions of supernovae and the powerful winds emanating from massive stars, produces massive outflows of hot gas. This gas is propelled outward, sometimes hundreds of thousands of light-years into intergalactic space. Is this material still considered part of the galaxy? It originated here, and some of it will eventually cool and fall back, recycling into the galaxy over billions of years. But some of it escapes forever, lost to the cosmic void. At what precise point does this ejected gas cease to be Milky Way gas and become, instead, part of the vast, diffuse intergalactic medium? The Magellanic Stream, a colossal ribbon of gas stripped from the large and small Magellanic Clouds as they orbit our galaxy, adds yet another layer of complication. This immense stream of gas stretches across the sky for approximately 600 Zalosan light-years. Is this gas still part of the Magellanic Clouds? Is it now part of the Milky Way? Or is it, in fact, neither, existing in a state of cosmic limbo, a transitional bridge between two gravitational systems? All three answers have their ardent defenders within the scientific community, highlighting the ambiguity of strict definitions. The approaching Andromeda galaxy poses the same fundamental problem, but from the opposite direction. Its immense dark matter halo might already be touching, or even interpenetrating our own. When two such colossal halos overlap, where precisely does one galaxy end and the other begin? The space between them, once thought to be truly empty, becomes shared territory, co-owned and gravitationally disputed. This is not merely an exercise in semantics. The definition we choose directly impacts our mass estimates for the galaxy. It affects how we compare the sizes of different galaxies. And, crucially, it profoundly influences our understanding of when the Andromeda collision truly begins. If the dark matter halos are already merging, then the collision, in its most preliminary, invisible form, has already been underway for millions of years. We are, quite literally, living inside it. Most astronomers, therefore, settle on pragmatic, operational definitions. The visible stellar disk ends where star formation effectively ceases. The dark matter halo ends at the viral radius, the point of gravitational binding. The dark matter itself extends as far as our most sophisticated computer simulations suggest, gradually fading into the cosmic background. Each definition serves different scientific purposes, providing useful frameworks for specific research questions. None of them, however, perfectly encapsulates the fluid, continuous reality of the cosmos. Here, then, is the profound truth: the Milky Way is not a singular, discrete object with sharp boundaries. It is, more accurately, a region, a vast zone of gravitational influence, a dynamic cosmic neighborhood. It possesses a dense, luminous core, a structured, intricate middle, and a diffuse, gradually fading edge. And beyond that perceived edge, it simply blends, slowly and imperceptibly, into something else entirely. The 200,000 light-year measurement is our current best answer, a reflection of our most advanced understanding. But ask that question again in 10 years or 20, and new measurements, new instruments, and new insights will undoubtedly change it. They always do. The galaxy has no absolute, definitive edge, because the universe, in its fundamental nature, simply does not operate that way. Everything blends. Everything connects. We live in a cosmos without hard borders, a vast, continuous tapestry of matter and energy. And we are still, patiently and persistently, learning to measure it, to chart its intricate contours, even as it constantly reveals its greater, more elusive truths. There are stars, at the very furthest reaches of our galaxy's immense halo, that are moving at truly insane speeds. We're talking velocities of 130 miles per second, 150 miles per second. Some even hit an astonishing 200 miles per second. By all conventional logic, these stars should have long since escaped the Milky Way's gravitational pull, flying off into the cold, desolate expanse of intergalactic space, forever untethered. Yet, they stubbornly remain. Some unseen force, continues to hold them in its silent, powerful grip. These celestial speedsters are known as high-velocity halo stars. It's important to distinguish them from hypervelocity stars, which move fast enough to definitively escape the galaxy entirely. Halo stars, by contrast, move just under that critical escape threshold, barely bound, perpetually skating on the razor's edge of cosmic freedom. Finding these elusive objects has been a monumental challenge. They are incredibly faint, immensely distant, and scattered thinly across a truly colossal volume of space. However, groundbreaking surveys, such as those conducted by the Gaia spacecraft, have meticulously tracked millions of stars with unprecedented precision. By accurately measuring their positions, their subtle motions across the sky, and their radial velocities, their movement directly toward or away from us, astronomers can calculate their precise three-dimensional velocities. Some stars, once their velocities were calculated, immediately triggered red flags, screaming anomalies in the data. One particular star, observed traveling through the outer halo, registers a breathtaking speed of 198 miles per second. The galaxy's calculated escape velocity at that specific location is, remarkably, roughly 200 miles per second. This star is, literally, a mere 2 miles per second away from breaking free forever, from leaving the Milky Way's gravitational influence. It's a cosmic rocket, barely held by the immense gravitational field, one small additional push away from absolute freedom. Why, then, do so many stars in the outer halo orbit so incredibly close to this escape velocity? This is not merely a matter of random chance, a statistical anomaly. Some profound cosmic mechanism must have placed them there, imparting that specific, critical amount of energy. But what could it be? Galactic collisions offer one compelling explanation. When the Milky Way, in its long, cannibalistic history, consumed smaller galaxies, these violent encounters injected immense amounts of energy into the system. Stars from the devoured dwarf galaxy, caught in the gravitational maelstrom, received powerful, velocity kicks, slingshotting them to extreme speeds. Some indeed achieved escape velocity and were flung into intergalactic space. Others, however, settled into these fast, barely bound orbits, now populating the Milky Way's halo as survivors of ancient, cosmic wars. The Sagittarius dwarf spheroidal galaxy, currently being torn apart by our galaxy, provides direct, ongoing evidence of this process. Its stars are scattering at high speeds as the Milky Way relentlessly tears it asunder. In a billion years, those scattered stars will be virtually indistinguishable from other native halo stars. Fast, ancient, and ultimately mysterious in their origin. But in this unique cosmic moment, we are witnessing the process unfold. Another intriguing possibility involves three-body interactions. In extremely dense stellar environments, such as the cores of globular clusters or regions of intense star formation, when two stars pass incredibly close to a third, massive object, perhaps another star or a black hole, the complex gravitational interactions can, in a cosmic slingshot effect, fling one of the stars outward at immense speed. While most such ejected stars would achieve true hypervelocity and escape the galaxy, a few might, by chance, land in that precise, sweet spot, moving incredibly fast but not quite fast enough to break free. They become the barely bound halo stars. Massive black holes further complicate everything, acting as powerful cosmic accelerators. If a star ventures too close to a supermassive black hole, the gravitational slingshot effect can accelerate it to truly enormous velocities. The supermassive black hole at the very center of our galaxy, Sagittarius A, weighs an astounding 4 million times the mass of our Sun. Any star that strays too close to its immense gravitational well faces one of two fates. Either it is devoured, swallowed whole by the cosmic maw, or it is violently flung away at incredible speeds. We have, in fact, discovered several true hypervelocity stars, objects undeniably leaving the galaxy at speeds exceeding 400 miles per second. Calculations meticulously trace their trajectories back to the galactic center, indicating that something near the black hole imparted that enormous kick. Perhaps they were once part of binary star systems, and the black hole captured one star while ejecting the other with immense force. But the barely bound halo stars, those that orbit far out in the halo, present a different, more subtle puzzle. They are not originating from the violent, energetic region near the galactic center. Their speeds are high, certainly, but not extreme enough to suggest a direct black hole encounter. They seem, in their cosmic dance, remarkably comfortable at the very edge of the galaxy's immense gravitational well. One compelling theory suggests that the dark matter halo itself is not as smoothly distributed as we often assume. Instead, it might be lumpier, containing concentrations or clumps of dark matter at specific distances from the galactic center. These localized gravitational enhancements could, theoretically, create stable orbital paths at high velocities, trapping stars in a kind of gravitational resonance. Stars might naturally settle into these orbits, explaining why so many halo stars appear to move at similar, high speeds. Testing this theory is, understandably, incredibly difficult. We cannot see dark matter directly, so we can only infer its distribution from the movements of visible stars. However, if the halo is indeed lumpy, we should, in principle, observe groupings or clusters of high-velocity stars orbiting together, perhaps subtly tracing the contours of these dark matter clumps. Some preliminary surveys hint at such groupings, while others find more random distributions. The data, as is often the case in frontier astronomy, is messy, complex, and open to interpretation. Here is what we know with absolute certainty: the outer regions of our galaxy are far wilder, far more dynamic, and far more complex than we ever expected. Stars move faster than simple models predict. The boundary between being gravitationally bound to the galaxy and escaping into intergalactic space is incredibly thin, a difference of barely a few miles per second separating eternal residency from cosmic freedom. If the galaxy is indeed larger than we previously thought, then an even greater number of stars reside in this precarious, dangerous zone, more objects perpetually skating at the edge, more potential escapees just waiting for a subtle nudge. And understanding precisely why they stay, why they remain bound against such immense odds, reveals something profoundly deep about galactic structure, about the nature of dark matter, and about the fundamental workings of gravity at truly enormous, cosmic scales. Fast stars at the very edge of the galaxy, held by invisible mass, moving at impossible speeds. And we are only just beginning to truly comprehend the mysterious forces that keep them here. The unsettling, yet ultimately liberating, truth that consistently emerges in modern astronomy is this: the Milky Way is not special. Every time humanity has dared to believe itself unique, to place itself at the center of the cosmic narrative, subsequent discoveries have gently, yet firmly, disabused us of that notion. And if we, with all our technological prowess and intimate proximity, manage to get the fundamental size of our own galaxy so spectacularly wrong, then the terrifying implication, the realization that keeps astronomers meticulously recalculating everything they thought they knew, is that we have, in all likelihood, measured Vol galaxies wrong. The entire cosmic census, the grand inventory of galactic sizes and masses across the observable universe, requires a profound and comprehensive rewriting. Every galaxy, it now appears, might be twice as large, or even more, than its recorded dimensions. Here is precisely why this monumental revision matters so deeply. Astronomers utilize galaxies as fundamental building blocks, as cosmic laboratories, to understand the universe at its grandest scales. How matter is distributed throughout the cosmos, how large-scale structures like galaxy clusters and filaments form and evolve, and, crucially, how the mysterious force of dark energy affects the accelerating expansion of the universe. If the galaxies, these fundamental units of cosmic structure, are universally bigger than we previously thought, then every single calculation built upon those assumptions is now subject to revision. Galaxy masses, for instance, are the primary determinants of how they interact with each other. Bigger galaxies, by definition, possess stronger gravitational fields. They are more effective at stripping stars and gas from smaller, less massive neighbors, engaging in more aggressive acts of galactic cannibalism. They dominate their local groups more completely, exerting a wider sphere of influence. They also cluster together differently, forming the intricate webs and filaments we observe in the large-scale structure of the universe in a subtly different manner. Recalculate galactic masses, and you inevitably recalibrate our entire understanding of galaxy evolution, from their birth to their eventual mergers and transformations. The problem extends even to distance measurements, a cornerstone of cosmology. Astronomers rely on certain types of galaxies, such as Type A supernovae in distant galaxies, as standard candles, objects with a known intrinsic brightness. By measuring how bright they appear to us, we can calculate how far away they must be. But if the host galaxies of these standard candles are, in reality, bigger and more massive, their intrinsic properties might also subtly change, affecting their brightness. This, in turn, would alter our calculated distances to them, which would then propagate errors through our measurements of the universe's expansion rate. Crucially, measurements of dark energy, the elusive force driving this accelerating expansion, are highly dependent on precise distance calculations. Any fundamental error in galactic sizes, therefore, cascades through every cosmological model, potentially shifting our understanding of dark energy's strength and distribution. The universe, it's possible, might be expanding faster or slower than our current galaxy size-dependent models suggest. Researchers are now painstakingly revisiting vast galaxy surveys, colossal repositories of cosmic data such as the Sloan Digital Sky Survey and the 2-micron All-Sky Survey, along with every other major astronomical catalog. They are applying these new measurement techniques, meticulously accounting for the presence and extent of dark matter halos, and utilizing stellar streams and the orbits of satellite galaxies wherever such data is available. Preliminary results from this monumental undertaking are, to put it mildly, disturbing in their consistency. Many galaxies, across a wide range of types and sizes, appear significantly larger than previously measured, some by a substantial 50%, others by an astonishing factor of 2. The trend is remarkably consistent. We have systematically underestimated the true scale of galactic sizes throughout the cosmos. Andromeda, our iconic neighbor, provides the clearest and most compelling example. The old measurement, for its visible disk, was approximately 220,000 light-years across. New, refined calculations now suggest a diameter of 300,000 light-years, perhaps even more, with its dark matter halo extending even farther. Andromeda, it turns out, is a giant even bigger than we had previously conceived, dwarfing its old estimates. Triangulum, the third largest galaxy in the local group, similarly grew from an estimated 60,000 light-years to nearly 100,000 light-years across. Smaller galaxies such as NGC 524 and NGC 2976 show similar, consistent increases in their estimated sizes. The pattern is undeniable. Every spiral galaxy examined so far has returned a larger, more expansive measurement. Why did this systematic underestimation occur? For precisely the same reasons we initially got the Milky Way's size wrong. Old measurement techniques predominantly focused on visible light, tracking the bright, easily discernible disks where stars are most densely concentrated. They largely overlooked the faint, diffuse outer regions where stellar populations are sparse but still gravitationally bound. And, crucially, they significantly underestimated the profound contribution of dark matter, whose invisible mass profoundly extends the galaxy's gravitational reach. The mistake, it seems, was not isolated but systematic, deeply embedded in the very methodologies and assumptions of an earlier era of astronomy. Modern instruments, however, have fundamentally changed the game. Wide, field surveys now map entire galaxies, from their luminous cores to their faintest, most diffuse outer edges. Infrared detectors possess the remarkable ability to see through the thick, obscuring dust clouds that previously hid vast swaths of galactic real estate. Deep exposure photography reveals incredibly faint outer stars and stellar streams that were utterly invisible to older instruments. Each successive improvement in observational technology and technique has inexorably extended the measured radius of galaxies outward, pushing the boundaries of our cosmic understanding. But the true breakthrough, the most compelling and undeniable evidence, has come from the meticulous study of satellite galaxies. Just as the Milky Way hosts dozens of smaller companions, other large spiral galaxies do as well. Andromeda, for instance, is orbited by dozens of dwarf companions. Triangulum has several of its own. By carefully tracking the precise orbits of these satellites, and then calculating the immense mass required to hold them in their gravitational embrace, these galaxies are, in essence, revealing their true, expansive sizes. Stellar streams, too, are now being discovered everywhere we look. Andromeda, much like our own galaxy, is currently in the process of devouring several smaller galaxies. The resulting streams of torn, apart stars wrap around it like shimmering evidence at a colossal crime scene. These streams, crucially, orbit far beyond Andromeda's visible disk, providing incontrovertible proof that its gravitational influence, its true extent, reaches far farther than old measurements ever suggested. Dark matter halos, it is now clear, extend to distances far greater than anyone had previously predicted. When one accounts for the full, pervasive extent of these halos, not just their inner, denser regions, spiral galaxies are revealed to be truly enormous, their spheres of gravitational influence reaching for hundreds of thousands of light-years. The space between galaxies, consequently, shrinks, making the universe feel more crowded, more gravitationally interconnected. This cascade of discoveries carries profound implications. Galaxy collision rates, for instance, now require a complete recalculation. If galaxies are universally bigger, their dark matter halos overlap more frequently, increasing the probability and frequency of gravitational interactions. The universe, in this new light, appears to be a more violent, more dynamic, and more gravitationally active place than we had previously imagined. Galaxy number density, the count of galaxies within a given volume of space, also shifts. The same volume of space, if each galaxy is larger, will contain fewer distinct galactic entities. This fundamentally affects cosmological models, shifting our understanding of how large-scale structures formed and evolved. It also changes predictions about how galaxy clusters, those immense gravitational groupings of hundreds or even thousands of galaxies, evolve over cosmic time. Galactic rotation curves, those perplexing plots of stellar velocities, now make far more sense. Many spiral galaxies, like the Milky Way, consistently exhibit flat rotation curves, with stars at the edge orbiting inexplicably fast. But if these galaxies are universally bigger, possessing more extensive and massive dark matter halos, then the rotation curves fit the observed physics much better. The pieces of the puzzle begin to align, and the fundamental laws of physics are preserved.